Alright, well in this video we're going to be discussing how we can implement regression in R. Now as part of this video, instead of working with some of the toy datasets that were present in our notes, I'm actually going to be working with a built-in dataset in R. So this dataset is called mtcars, and the first command I'll run is head mtcars to look at the first thing that's in cars. Now, because this is a built-in dataset in R, you can actually use the question mark notation, question mark mtcars, just like you would with a function, to get a little bit more information about the dataset. So this is from MT Motor Trend, 1974. And we've got 32 automobiles in here. We've got miles per gallon, number of cylinders, the displacement of the engine in cubic inches, horsepower, real axle ratio, weight, quarter mile time, engine, the type of engine, so this is categorical and it's coded as binary. Transmission, also categorical, coded as binary. And then number of forward gears and number of carburetors. So this is what we're going to be working with, and ultimately we're going to be trying to predict the miles per gallon. Now, we're going to go through this. We'll do the simple linear regression, and then we'll kind of, maybe in a different video, but continuing along these same problems, we'll work on the multiple linear regression. And we're going to start by trying to predict miles per gallon using the quarter mile time. So what I'm saying is that I think that the quarter mile time is somehow related to miles per gallon. Perhaps cars that have slower quarter mile times are going to have a better miles per gallon. Now the first thing that I'll do is I'll plot this. Now there's a couple of different ways to plot it. You can give it X and then a variable, and Y and then a variable. You can also use something like our formula format that we used for ANOVA, where I actually give it the miles per gallon as my outcome, and then the squiggle, and then my independent variable. And I'll tell it what data set to use, mtcars. And this will give me a plot of my data set. Now there's many ways to clean up this plot. I'm not going to focus on them in this video, but what I will just point out is the axes labels, the quarter mile in seconds, and the miles per gallon. And it seems, actually, this is kind of the opposite of what I thought. I thought, oh, actually, no, never mind. This is right. I thought that as the quarter mile time gets slower, the miles per gallon increases, and that does seem to be true. Our better engines are having worse miles per gallon, by and large. All right, so this relationship looks roughly linear, and this is what I'm trying to plot. So how do I actually fit the linear model? Well, I fit my simple linear regression model using the LM command. That stands for linear model. I give it the same formula that I normally do, the output or dependent variable y, squiggle, and then my x variable, q-sec, in this case, quarter miles in seconds, then data equals mtcars. And I can run this line, and I'll get my parameter estimates for each of the pieces. It's not giving me a full output because, again, in R, you know how R is. It doesn't give you the full output right away. So what I'll want to do is save this as a mod. Maybe I'll call this SLR mod for simple linear regression model. And then I can use this later on. Now, one cool thing that I can do with the simple linear regression model is I can plot the regression line. So I use the command AB line and then give it my model with my regression line. And this is going to add the simple linear regression line onto my pre-existing plot. So I have my plot command. That's what put all the data points on there. Once I have all the data points on there, I can use AB line and then my LM, my linear model, simple linear model in this case, to add that linear model line onto the plot. So I can see that there's a positive slope, a positive relationship between q-sec and mpg. Now, is this positive relationship just for my sample, or is this for the population, the whole population of cars? Well, that's what my statistical tests are going to tell me. So remember, before I do any kind of interpretation of positive or negative or large or small or any kind of interpretation at all, first I have to look at my significance tests. So I'm going to use the summary command to look at my significance tests for SLR mod. Looking at these, I can see that my intercept is not statistically significant, but my slope is statistically significant. So this is good. This lets me know that I can go on and interpret the slope as in my normal interpretation method. So again, this indicates the slope here indicates the 1 unit or the number of units of increase in y for every unit increase in x, and that's a super boring and statsy way of talking about it. In our problem, what this is saying is how many miles per gallon do I increase on average when my quarter of a mile in seconds time increases by a single second. So as a car has a slower quarter mile time by 1 second, on average, the car's miles per gallon is going to be about 1.4 miles per gallon better. So this is a really useful interpretation. And again, the big takeaways are that it's positive. That is, as my quarter of a mile time increases, as the cars get slower, the miles per gallon also increases. So that's what the positive estimate says. And it's statistically significant. So I have reason to believe that this is not 0. All right, so that's kind of it. That's our simple linear regression model. Now we talked about a few other things here that we can do real quick. So calculating the sum of squares was one of them. So previously we used ANOVA or the AOV command. I'm going to use the ANOVA command. The ANOVA command is specifically for pulling out ANOVA objects in regression. It's not really meant for the analysis of variance that we talked about as an analysis in and of itself in class. So I wouldn't really use the ANOVA command for that, but for creating an analysis of variance table for regression, it works perfectly. You'll note that my p-value is identical in these two cases to within rounding, and my t-value squared gives me my f-value. So this, we said, was always true for simple linear regression. I also get my sum of squares. Now I don't have my sum of squares total, but remember the sum of squares total is the sum of squares from my model plus the sum of squares residual. So I can add those two together to get my sum of squares total, and then take my sum of squares from the model divided by the sum of squares total in order to get my my coefficient of determination if I wanted to. Another way that you can get that is actually by pulling off of the summary objects. So let me show you what I mean. Coefficient of determination. So I get my summary of SLR mod, summary SLR mod. And looking in here, I actually see it gives me a multiple r squared. So I have that coefficient of determination right in that output, and I have the adjusted r squared. If you didn't want the whole output, you just wanted that component, you could use a $sign and then do r dot squared to just pull out that r squared value. But usually what I'll do is I'll run all the output, and then when I'm ready, I'll just look down here for the r squared. Incidentally, one other thing you'll notice that r does, which is pretty nice, is it does the overall f-test as part of the basic regression output. So you don't have to run this whole ANOVA table. You can just quickly look at this bottom line in your basic regression output to see what your f statistic is, what the degrees of freedom are, and what the p-value is for the whole model. Again, in simple linear regression, this isn't particularly useful because that p-value is going to be the same thing as the p-value for a slope of our only independent variable. But within a multiple regression situation, that is going to be really useful because it tests all of the independent variables at the same time. All right, so for calculating the correlation, well, for correlation, there were a couple of ways to do it, so I'll do correlation. Recall that we talked about just taking the square root of our coefficient of determination, so SQRT is how I take the square root. So this is the correlation between my values. I could also just use the core command, core, and then mtcars $ miles per gallon, and mtcars $ Cusack gives me my correlation between those two, and you'll see both of those methods match. You can use either one. The top one is what we talked about in class. The bottom one is, if I were looking for a correlation, honestly, the bottom one is how I would do it. All right, well, let's talk about prediction for a little bit. Or excuse me, let's talk about confidence intervals and prediction. So for confidence intervals, these are pretty easy to put together. So for confidence intervals, I use the confint command. It stands for confidence interval. And then I give it my model, SLR mod, and it's going to give me a 95% confidence interval for each of these values. If I wanted it to be something different than a 95% confidence interval, let's say I wanted it to be like a 90% confidence interval or something, I can give it the level and set that equal to 90, and this would give me a 90% confidence interval instead of a 95% confidence interval. So this gives me confidence intervals for both the slope and the intercept. I see the intercept has 0 in it, so not statistically significant. We saw that with our p-value. And the slope does not have 0 in it, so statistically significant. And we also saw that with our p-value. People sometimes prefer confidence intervals to just a p-value because the confidence interval gives that reasonable range of values. I can see actually that even though my p-value is statistically significant, this gets pretty close to 0. So maybe it's not too far out of the realm of possibility that my slope is not actually positive. Maybe it's 0. In fact, I could do a 99% confidence interval, and it looks like for a 99% confidence interval, I wouldn't have enough evidence to reject. I wouldn't have enough evidence to reject at the alpha equals 0.01 level. Actually, you see that with the p-value here too. Anyway, so that's how I can construct confidence intervals for my parameter estimates. Now we talked about two kinds of confidence intervals. Confidence intervals for the parameters, so this is like for beta 0 and beta 1. But then we also talked about doing a confidence interval for prediction, where we were trying to predict a value, and we wanted to get a reasonable range of values that the group mean could fall in. So for predicting, I use the predict command. So for predict, I have to give it my model, and then I have to give it new data. So I'll write comma new data equals. Now what's weird about the predict command is the new data has to be in a data frame format. Has to be this way. And when I give it my new x value, or if I'm using multiple regression, if I give it new multiple x values, I have to write the independent variable name qsec, and then I have to write equals and then whatever that is. So in this particular case, I'll use qsec equal to 15. So a 15 second quarter mile, that's pretty short. I can look at my plot and see what the quarter mile time is. So 15 puts it like right at the top of the cars that I looked at. And I can see that I would predict the miles per gallon of such a vehicle to be right around 16 miles per gallon. That seems to match with my plot as to where my line would say 15 miles per gallon would fall. Now, if I had multiple independent variables, I'd write a comma, and then I'd have to write the second IV equals whatever I want that to equal, and so on and so forth. But that's what's necessary to create a prediction in R. Actually, I think it's a little bit irritating unless I'm doing a lot of these. So for the prediction, it might almost be easier to just look at your model, SLR mod, look at these values and kind of plug it in by hand. Maybe not quite easier to do it that way, but it's not that much more efficient to do it in R. I guess this is nice if you have really a lot of numbers, and it's nice because once you have it, you can just copy and paste it over and over and over again and just replace that number with whatever you're looking at. All right, so we talked about how when we do prediction, we can actually come up with intervals. So we talked about a confidence interval, and we talked about a prediction interval. We said we used a confidence interval for prediction when we're trying to get a reasonable range of values for a group mean for that prediction. So the command that I use to type this in is interval. So I'll do comma, and I'll make sure the comma is after the closed parentheses of the data frame, but still inside of the parentheses for the predict command. And then in quotes, I'm going to put either confidence for a confidence interval of prediction, or I'm going to put predict or prediction for a prediction interval for the prediction. And again, confidence interval, that's our group mean. Where's the reasonable range of values to expect the group mean to fall? The prediction interval is looking at an individual value. So in this case, I'd say, what would this mean? Well, this would mean if I had a new class of cars that was coming out with a 15 second quarter of a mile time. On average for that class of car, what will the miles per gallon be? So what's the average miles per gallon for that whole group of cars? This second one, the prediction interval, says for an individual car, I have an individual car coming out that's that does a quarter of a mile in 15 seconds. What's a reasonable range of values to predict the miles per gallon to be for that car? And again, you see this is a much wider range than what we get for the group mean prediction. That's because individuals have a much higher variability than the group means do. All right, so the last thing we'll talk about in this video is the residuals and looking at them. So how do we pull these out of our model? Well, once we have the models fit, we can use the resid command. So I'll do resid of SLR mod. And I'll just highlight this and run this line to show you what it does. It gives me the residual for each individual value or each individual car. I'm going to save this as a variable called res. Now this is how I get the raw residuals, but we talked about that sometimes it's nice to have the standardized residuals. So standardized residuals, I'll save this as std res. And all I do is I use a command called scale. So whatever I put into scale is automatically going to be standardized. So if I put my raw residuals into scale, now I have standardized residuals. And it really is that easy to create standardized residuals. I start with my raw residuals, and then I use the scale command to turn them into standardized residuals. And that's kind of it. For the residual versus prediction plot, so this is one of the ways that we talked about testing for, so check the homogeneity variance, that is the equal variance across everything. And we can use this to check outliers. I would plug in, I'd want to make a plot with my y-axis being my standardized residuals, and my x-axis being the predicted y values. Now we talked about how to predict an individual y value up here, and so the question is, how do I predict a whole bunch of y values? Well, I can predict a whole bunch of y values using the predict command and then not giving a specific value. So if I do predict and then just give it the model, it's going to give me a prediction for every single car in that model. It's not going to specify which car I'm talking about. It's going to predict all of them. So if I run just the predict command and then the standardized residuals, this gives me my residual plot. Now if I want to make it a little bit fancier, I could do something like AB line, so this adds a line, and H equals 0, so I'm going to add a horizontal line at 0, and then I'll do LTY, which stands for line type, and write dashed. And so this is going to give me a fancy dashed line at 0 that we did kind of see in some of our plots in the notes. It's kind of nice to have this horizontal line at 0. Here I see there's a couple of residuals that are peeking around 2. These might be outliers, but honestly, they don't look particularly large. I don't really see any patterns among these residuals. You could argue it's getting bigger and coming back down, getting bigger, coming back down, but honestly, I don't really see it. This looks pretty random to me, so I'm not going to be too worried about these residuals. They actually look fairly good in this case. No outliers to speak of. Maybe one, but nah, not really. And then doesn't look like any patterns as far as increasing residuals or decreasing residuals or anything like that. All right, so for our last plot, I think I mentioned we would be talking about this plot in the video, that this is one that wasn't covered in our notes. It's called a QQ plot, and this is how we check normality. So for a QQ plot, what I'm going to do is I'm going to use these standardized residuals that I just made and use the command QQnorm to create this QQ plot. So I'll give it QQnorm and then my standardized residuals. And then I'm going to add a line, AB line, and I want my line to start at 0 with a slope of 1. And this is going to add a diagonal line onto my normal plot. Now these can be a little tough to interpret. They're easy to feel like that there's a problem. So the idea is that the dots should follow along the line roughly. Now you see that there's kind of some variability going on here. So one might say, oh, well, it goes off the line. Actually, this looks pretty good for the amount of data we have. It's not too bad. And so all I want to do is make sure that all my dots are along this line, and this helps me determine if the data are normal or not. Now this can be kind of hard to do. So within the car package, there is actually a, within the car package, there's actually a QQ plot that's built into here as well, std res. And when I run this QQ plot, it actually gives me a confidence interval where I can see for the confidence interval if the dots fall within the line. So I do have a little bit of area of concern up here. I personally wouldn't be too worried about this. It's just a few dots. They don't seem to be particularly problematic. And using this confidence interval can be a little bit easier to read these. I can see that all of these other dots are well within my blue area. I'd be concerned if they go outside of the blue area. Again, you could make the argument that some of these in the top here are far enough outside the blue area to be of concern. I personally think that they look fine, but that's one thing you could do. If we determine that these were of concern, that doesn't mean that my predictions for the parameter estimates are wrong, but it does throw into question my statistical tests. So I'd want to be a little bit careful about those statistical tests and basing anything on them. All right, so this is our down and dirty way to do regression and all the different pieces we talked about for simple linear regression in R. Actually, our multiple regression, depending on where you're watching these and what order you're watching these in, multiple regression will pick up from here, and we'll keep going, building on these models that we talked about today.